Welcome to this explainer. Today, we're diving into some absolutely fascinating concepts from Chapter 5 of Designing Data-Intensive Applications. So I want you to think of your application data as a time traveler. Seriously, in modern, highly available systems, your data is constantly navigating its way through different software versions, crossing network boundaries, and surviving totally unexpected system crashes. And it has to survive these journeys completely intact. So if you've ever wondered how large-scale systems evolve their data structures without everything immediately breaking, well, you're in exactly the right place. Here's our roadmap for this explainer. We'll be covering 1. The rules of time travel, 2. The language of data, 3. Schemas and binary heavyweights, 4. Data flow through databases, 5. Services and durable workflows, and finally, 6. Event-driven architectures. Let's jump right in.
Section 1. The rules of time travel, navigating schema evolution.
Okay, so the core tension in practically any modern system is this baseline expectation of zero downtime. Because we're constantly doing rolling upgrades, old and new code just have to coexist. Schema evolution isn't just some nice-to-have best practice, it's honestly a biological necessity for your application's survival. Your business requirements are going to change, your data shapes will mutate, and your system absolutely must adapt safely. Otherwise, your application is going to stagnate, or worse, it'll just break entirely the second a new field is introduced.
To actually survive this mutation, we need some strict rules for our time-traveling data. First up, we have backward compatibility. This just means newer code must be able to read data written by older code. And this is generally pretty straightforward, right? Because you, the author of the new code, already know exactly what the old data looks like. But then we have forward compatibility, which is way trickier. This means older code must be able to read data written by newer code. And critically, it has to be able to just ignore any new additions without throwing errors or dropping data.
Moving on to Section 2, the language of data, text versus binary.
Whenever data leaves your application's memory to travel across a network or get saved to a disk, it needs an encoding format. But here's the thing. We accept a pretty massive trade-off when we use familiar text formats like JSON, XML, and CSV. Sure, they are ubiquitous and wonderfully human-readable, which we all love, but they're inherently flawed for really high-performance systems. XML is famously verbose. CSV completely lacks a schema, which just leaves parsers guessing. And JSON? Well, JSON has this notorious ambiguity with numbers. Because it doesn't actually distinguish integers from floating-point numbers, parsing numbers greater than 2 to the 53rd power can literally result in precision loss in languages like JavaScript. Think about a massive 64-bit post ID on X. This flaw forces developers into hacky workarounds, like having to send the exact same ID twice, once as a number and once as a string.
So, knowing all that, you might think binary encoding is the silver bullet. Take a standard JSON payload and convert it into a binary format called MessagePack. Sure, it reduces the payload down to 66 bytes, which definitely saves some space. But if you look closely, you still have all these string labels in there: username, favorite number, interests. Without a strict external schema, the data is still dragging along all this unnecessary baggage. You're still explicitly naming every single field and every single record you send over the wire.
That brings us to Section 3. Schemas and binary heavyweights, protobuf and Avro.
Google's protocol buffers, or protobuf, solves his verbosity problem incredibly elegantly. Instead of seeing field names taking up precious byte space, you use explicit field tag numbers like =1, =2, and =3. And this is exactly how protocol buffers achieves that graceful schema evolution we talked about earlier. If older code encounters a brand new tag number that it simply doesn't recognize, it just uses the data type annotation to skip exactly that many bytes. Boom. Forward compatibility is achieved flawlessly, and you don't lose anything or crash on unknown data.
Now, let's contrast protobuf with Apache Avro. Protobuf relies on the exact same schema being available at both encoding and decoding, using those tag numbers to bridge any gaps. But Avro, which was originally built for Hadoop, takes a totally different path. In Avro, there are no tag numbers at all. Instead, decoding actually requires two schemas. You have the writer's schema, which was used to encode the data, and the reader's schema, which is what the application actually expects to see.
The really crucial point here is how Avro dynamically resolves the differences between these two schemas. It essentially maps a writer schema directly to a reader schema. So if they're slightly different, say maybe a field was added or aliased, Avro just automatically translates the data on the fly. This tagless approach makes Avro incredibly powerful for dynamically generated schemas. For example, if you're dumping a relational database to a file and those database columns shift over time, Avro just dynamically matches up the column names on the read side. No manual tagging required whatsoever.
Section 4. Data flow through databases, writing to the future.
All right, so now that we know how data is packaged, where is it actually traveling? Well, the most fundamental destination is the database. And I really want this quote to sink in. Storing something in the database is sending a message to your future self. Think about it. When your application writes a record today, the version of the application that reads it tomorrow, or maybe next year, might be entirely different. Because of this, backward compatibility is absolutely non-negotiable. If you break it, you have essentially encrypted your own data against your future self. Databases handle this evolution primarily by filling in default values for missing columns, which completely avoids the nightmare of having to rewrite terabytes of historical data every single time you tweak a schema.
Section 5. Services and Durable Workflows, Present-Day Conversations. Moving out of the database and onto the live network, we run into the two dominant paradigms for synchronous service communication, REST and RPC. REST leans heavily on HTTP. It treats state transfer as distinct from function calls, and it's basically custom-built for public APIs. RPC, or Remote Procedure Calls, goes a different route. It tries to hide the network entirely, making a remote request look just like you're calling a local function in your own code. But RPC faces some really distinct challenges. The network is wildly unpredictable, you've got latency spikes, packets dropping out of nowhere, and translating data types across different programming languages can get incredibly messy. When data travels synchronously, you always have to account for these unpredictable network realities.
To manage all that network unpredictability across multiple services, engineering teams increasingly rely on workflows and durable execution. Let's trace a payment system as it routes through fraud checks and bank deposits. In a highly distributed architecture, simply wrapping all of this into traditional database transaction just isn't possible. Durable execution frameworks, think of tools like Temporal, solve this by meticulously logging every single RPC call and state change. So if a node crashes right before the credit bank account step, the framework just restarts the task, skips the steps that already succeeded, and resumes perfectly. It essentially enforces exactly once semantics for your data's entire journey.
And our final section, Section 6, Event-Driven Architectures, Asynchronous Messaging. So instead of making direct, synchronous RPC calls, systems can route their data through message brokers, which gives you vastly superior architectural flexibility. A broker basically acts as a giant shock absorber. If the receiving service gets temporarily overwhelmed, the broker just buffers the data. It prevents message loss, it completely removes the headache of one service needing to know the exact IP address of another, and it allows a single data event to be seamlessly fanned out to multiple downstream consumers at once.
Just look at this recovery process in action. We've got a message broker safely redelivering message M3 to consumer 1 after consumer 2 suffered a crash right in the middle of processing. This complete decoupling handles system failures incredibly gracefully. And when you combine this with techniques like change data capture, which is where we take standard database writes and turn them into a continuous stream of events, we can keep search indexes, caches, and analytics databases perfectly synchronized in real time. And that happens no matter what kind of localized failures occur along the way.
We've seen today that data isn't just some static thing. It's a traveler, moving through time. It's enduring code upgrades, navigating totally unpredictable networks, and recovering from sudden node crashes. We've explored the rules of compatibility, the sheer efficiency of binary formats like protobuf and Avro, and the awesome fault tolerance of durable workflows and asynchronous brokers. All of which leaves us with one final, very important thought. As your own business requirements mutate and your applications inevitably evolve, is your data structurally prepared to survive the journey? Thank you so much for joining me on this explainer, and I really hope this empowers you to go out and master your own distributed data systems.